In this video, I'll go through some calculations of eigenvalues and eigenvectors. So the eigenvalues of a matrix A are the roots of the determinant of lambda I minus A. I here is the identity matrix, and then the eigenvectors are the solutions of lambda I minus A times a vector x set equal to the 0 vector. So I'm not going to go through the details of why eigenvalues and eigenvectors might be useful. This video is purely going to go through the mechanics of calculating these things. So let's start with this example here. A equals minus 2, 3 in the first row, minus 4, 5 in the second row. First thing I need to do is calculate the determinant of lambda I minus A. So what is lambda I minus A? Lambda I is the constant lambda times the identity matrix. So lambda 0 in the first row, 0 lambda in the second row, and then I subtract the A matrix. So that's going to be lambda plus 2 and then minus 3 in the first row, 4, and then lambda minus 5 in the second row. I showed how to calculate determinants in another video, so in the 2 by 2 case we multiply these two, lambda plus 2 and lambda minus 5 together, and then we subtract 4 times minus 3, so we subtract minus 12, so that's equivalent to adding plus 12. If I multiply this out, I'm going to have lambda squared. I'll have plus 2 lambda minus 5 lambda, so minus 3 lambda, and then I'll have minus 10 plus 12, so plus 2. And it turns out that I can factor this equation, which is nice, into lambda minus 1 times lambda minus 2. So this is called the characteristic polynomial, and if I set that equal to 0, that's the characteristic equation. Let's try that again. I'm going to set this equal to 0, and to make this equation 0, lambda could be 1 or lambda could be 2. So those are my two eigenvalues. Lambda 1 is 1 and lambda 2 is 2. So next I'm going to write down what this matrix looks like when lambda equals 1. So lambda 1I minus A is going to be lambda plus 2 will be 3, and then minus 3, and then 4, and then lambda minus 5 will be minus 4. So now I need to solve this equation here, this vector equation. And I've written down what my matrix looks like. It's 3 minus 3, 4 minus 4. So if I row reduce this matrix, then that will give me a solution to this equation. So let's row reduce that matrix. If we do that, and I'm not going to go through the details here in the interest of time, I'll just jump to the punchline. I'll end up with 1 minus 1 in the first row and 0, 0 in the second row. So that first row, what that means is that x minus y equals 0. So if I was to set y equal to t, then x is also equal to t. So my eigenvector here is 1, 1. X and y are both the same. Let's go through the same process for lambda 2 equals 2. My matrix in this case is going to be lambda plus 2 will be 4, and we'll still have minus 3 and 4 there, and then lambda minus 5, so 2 minus 5, so I'll have minus 3 here. Okay, if I row reduce that matrix, I end up with 1 minus 3 over 4, and then 0 and 0. So that means that x minus 3 over 4 y equals 0. Again, I'm going to set y equals to t, and then x will be equal to 3 over 4t. So my eigenvector in this case, I'm just going to do a little bit of side work up here in the corner. If I set y equal to 1, then x would be equal to 3 over 4. But it's nice sometimes not to have fractions in vectors, and so an eigenvector we can just multiply it by any constant and it remains an eigenvector. If you just think of what the definition of the eigenvector is, multiplying x by any constant will still result in solving this equation if x is an eigenvector. So to avoid fractions, I can multiply that eigenvector that we've just found by 4. So 4 times 3/4 would be 3, and 4 times 1 would be 4. So there's the eigenvector without fractions. So that's the end of that problem. We found the eigenvalues and the eigenvectors. How about a 3 by 3 example? So how about for this 3 by 3 matrix A here? First step, figure out the determinant of this matrix, which I've written out here. So we've got lambda minus 1, minus 2, 1 in the first row, and so on. If I do a whole bunch of algebra, I'll end up with this nicely factored equation here. And then if I set that equal to 0, that tells me that lambda 1 is equal to minus 1, and lambda 2 is equal to 0, and lambda 3 is equal to 2. And then let's find the eigenvector corresponding to lambda 1 equals minus 1. So I've got my equation here that I need to figure out, and so if I find this matrix lambda I minus a and then row reduce it, I'll be able to find the eigenvector. So let's do that, and what we end up with for the first eigenvalue is 1, 0, 2 in the first row, and then 0, 1, and then minus 5 over 2 in the second row, and then zeros in the third row. And so the first row means that x plus 2z equals 0, and then the second row means that y minus 5 over 2z equals 0. So if I set, in this case, z equal to t, then we'll have that x is equal to minus 2t and y is equal to 5 over 2t. So again, I'm gonna just do a little bit of side work, or corner work, I guess. I'm gonna use this corner. So my this is just like rough work. So I'm looking for the eigenvector, and if I have z equal to 1, so t is 1 in this case, then y would be 5 over 2, and x would be minus 2. And so if I want to avoid fractions here, then I could multiply each of these elements by 2. So my eigenvector without fractions would be minus 4, and then 5, and then 2. Okay, second eigenvalue, lambda 2 equals 0. If I row reduce lambda to I minus a, I get 1, 0, 1, and then 0, 1, minus 1, and then I get zeros in the third row. So now x plus z equals 0, and x, no, not x, y minus z equals 0. Again, I'll set z equal to t, and then this time we've got x equals minus t and y equals t. So if t was equal to 1, then z would be 1 and y would be 1 and x would be minus 1. So there's the eigenvector for the second eigenvalue. And then the third one, row reducing that matrix, we get 1, 0, minus 1, and 0, 1, minus 1, and then 0, 0, 0. So x minus z equals 0, and y minus z equals 0. Set z equal to t, so then x is also going to be t, and y is also going to be t. The eigenvector in this case is just 1, 1, 1. Okay, so that's the second problem solved. What about the third one? What about this matrix A here? So the characteristic polynomial for this equation, for this matrix, ends up being lambda plus 3 squared times lambda minus 5. So the eigenvalues, well, it looks like there's just two of them, minus 3 and 5. But because lambda plus 3 is squared in this characteristic equation, we say that that first eigenvalue, lambda 1 equals minus 3, has multiplicity 2. Multiplicity 2. Okay, let's go through the next step. So the next step is to row reduce lambda 1 I minus a, and we end up with 1, 2, minus 1 in the first row, and then the other two rows are all zeros. So that means that x plus 2y minus z equals 0. So we're going to need two free variables in this case. Let's say y equals s and z equals t. And then x would be minus 2s plus t. So our eigenvectors, so x is going to be minus 2s plus 1t. So that's y will be s, and then z will be t. So there's our two eigenvectors, minus 2, 1, 0 and 1, 0, 1. So we've got two eigenvectors for this eigenvalue, and that was the eigenvalue that had multiplicity 2. And for the second eigenvalue, lambda 2 equal 5, our row reduction leads to 1, 0, and then 1/3, and 0, 1, and 2/3, and then zeros in the last row, and so x plus 1/3 z equals 0, and y plus 2/3 z equals 0. So if I set z equal to t, then x equals minus 1/3 t and y equals minus 2/3 t. So I'll just do a little bit of side work here. If t was 1, then we would have minus 1/3 for x and minus 2/3 for y. But if we want to avoid fractions, we can multiply through by 3. So our eigenvector is going to be minus 1, minus 2, and 3. So there's a few examples of calculating eigenvalues and eigenvectors.